2023, cosmologists announced that they had detected the faint signals of a gravitational wave background, a feat never before accomplished. This gentle echo of ripples in space-time has long been theorized by physicists, but only detected for the first time this year. This is a major moment in cosmology. But what exactly is this wave background, and why is this discovery so significant? To find out, we first need to travel more than a century back in time, to the life's work of one of history's most celebrated minds. Published in 1915, Einstein's general theory of relativity provided a revolutionary description of gravity. And then, based on this theory, he went on to predict the existence of gravitational waves, ripples in space-time. Although at times he also rejected the idea. Here is where this particular field in physics really starts to open up. Although, surprisingly, some pre-Einstein scientists had already proposed the existence of these waves. Originally, the concept was derived from the laws of electromagnetism. In the 1860s, James Clerk Maxwell formulated equations that formed the foundation of classical electromagnetism. He unified electricity and magnetism, discovering that they were two sides of the same phenomenon, and that they traveled through space as waves at the speed of light. Maxwell's discovery had serious implications across physics, and Maxwell himself pondered whether we can similarly describe gravity via fields. Next, and the first to follow up on this, was an electrical engineer named Oliver Heaviside. In his 1893 paper, A Gravitational and Electromagnetic Analogy, Heaviside directly compared gravitational and electromagnetic fields, wondering whether gravitational fields similarly propagate at the speed of light. If so, the movements of attracting bodies would result in disturbances in the gravitational field, traveling at a fixed velocity. More than 20 years prior to Einstein then, science had already pushed itself to the edge of this major discovery. In hindsight, this research is truly astounding, but then the repercussions of it really came into view. Einstein's theory of special relativity was published in 1905. Special relativity posited that the speed of light in a vacuum is the same, regardless of the motion of the light source or an observer. In short, this means that nothing, not even gravity, can move beyond the speed of light. While Einstein was working on special relativity, however, the French polymath Henri Poincaré developed a lot of similar mathematics independent of Einstein. And in his 1905 paper, On the Dynamics of the Electron, he pondered the laws of gravitation. Poincaré again tried to understand gravity using the principles of electromagnetic fields, and assumed that gravity propagates at the speed of light. The result of this is a time delay between gravitational changes and their effect. Poincaré's major point was that these changes are propagated by gravitational waves. Unfortunately, he did not expand on their nature, but was amazingly correct in this assumption. A decade later, Einstein published his famous paper on general relativity. This described gravity as a geometric property of space-time, but didn't mention any sort of cosmic vibrations. We're getting closer, but not quite there. And in fact, in 1916, Einstein reportedly wrote in a letter to the German physicist Karl Schwarzschild that, quote, "There are no gravitational waves analogous to light waves." 2 years later, Einstein published a follow-up paper on the topic. Within the paper, he shows a change of heart toward the idea, and subsequently incorporated the concept of gravitational waves into his theory. And broadly, how Einstein explained them is still how we think of these waves today, as infinitesimally small distortions in space-time, which transport energy as gravitational radiation. Today, this breakthrough is still remembered as an incredibly impressive feat, especially since he had no way of observing this phenomenon. Disappointingly, though, after a few decades, an older Einstein began to reject gravitational waves. Indeed, he changed his mind on them throughout his life. As it turned out, this was due to an error in his calculations, which was spotted and fixed by the American mathematician and physicist Howard P. Robertson. The confusion had created a temporary stigma around the topic, though, and there was something of a dark period in its research. Thankfully, technology has now come a long way since Einstein's day, and we now know that the waves are there, even if they are exceedingly tough to detect, requiring extremely sensitive equipment. In the 21st century, gravitational wave astronomy has certainly started to flourish. In 2015, the first ever successful observation of a gravitational wave was made, achieved thanks to the Laser Interferometer Gravitational Wave Observatory, or LIGO. Back then, what the researchers detected was a gravitational signal emitted from the merging of two black holes. Interestingly, this was also the first black hole merging period ever observed. In the context of gravitational waves, however, the intensity of the event created gravitational radiation with more energy than all of the observable stars in the universe emitted as light in the same time frame. And finally, this detection was the crucial first step in finding the aforementioned gravitational wave background. Also called the stochastic background, the gravitational wave background is a relic of the gravitational radiation left behind from the very early years of our universe. This creates something of a hum, permeating throughout the entire cosmos, caused by various events. One such event is, of course, the Big Bang itself, which is likely to have produced the majority of the hum. These waves would have likely been made in the universe's first seconds, and will have since stretched with the cosmos's expansion. They've simply always been here. Theoretically, the stochastic background should be a continuous noise which is ubiquitous and homogeneous across all of nature. And that's why the quest to find it has gotten so many excited. Researchers believe that studying these universal cosmic ripples could give us insight into the very earliest moments of the universe. We could learn about mind-blowingly ancient processes that are inaccessible via all other methods. The good news? In 2023, we successfully detected what has been referred to as the universe's cosmic harmony. It was announced in June by the North American Nanohertz Observatory for Gravitational Waves, an international consortium of astronomers who drew on observations from radio telescopes around the world. They were able to reach their results by analyzing approximately 15 years of pulsar data. A pulsar is an extremely magnetized rotating neutron star that emits intense beams of electromagnetic radiation from its poles. They're created in supernova explosions of massive stars, but we can measure them when they just so happen to point towards Earth. This allows us to calculate their rotational periods, which can be amazingly short, ranging from milliseconds up to around 8 seconds. 15 years of data on 67 pulsars was compiled and used in the study. The underlying principle was to treat the pulsars as reference clocks that send out regular signals monitored on Earth. Theoretically, if a gravitational wave were to pass through our line of sight to the pulsar, the local fabric of space-time would be perturbed, altering the observed pulsar rotational frequency. Even though pulsar-emitted electromagnetic radiation spends hundreds to thousands of years traveling through space, the detectors we have on Earth are able to measure perturbations of less than a millionth of a second. Back in 1983, astrophysicists Richard Hellings and Alan Downs produced a prediction for what these waves might look like in a model called the Hellings and Downs curve. That 15-year dataset then provided clear evidence of an isotropic background of gravitational radiation and gave the first real-life measurement of the Hellings and Downs curve. Currently, the specific sources of this background is undetermined and requires further research. Observatories hope to someday observe the gravitational rhythm of the first trillionth of a second of the universe's existence. This would allow cosmologists to witness, in a way, the birth of our universe, almost 14 billion years later. While it's been over a century since Einstein's great prediction of these ripples in the cosmos, we're only just beginning to see the tip of the gravitational wave iceberg. For now, the future is bright for the field, and we can expect this research to continue to answer the mysteries of the origins of the universe. So watch this space.